Topic 2.2 leads us again into Unit 2 a little bit more abruptly because we're leaving the idea of sequences for a second and transitioning into exponential functions. But this is a transition lesson. So last section, we learned that arithmetic sequences behave like linear functions. So that is one of the things we learned. Arithmetic sequences were the ones that went up or down with addition or subtraction. So they behave like linear functions. They have a common difference, which acts like the slope, and we had different formulas for that. We also learned that geometric sequences behave like exponential functions. And we haven't gone over all of that much about exponential functions in this class, but you do have some prior knowledge from previous classes of what exponential functions do. Today we're going to really nail down the relationship between these types of sequences and the linear and exponential functions. So this first table here with these formulas for you compares the arithmetic sequences with linear functions. So I have the two formula types that I sort of talked about last class, calling it slope-intercept or point-slope form. And let's point out the important things. Looking at the linear function side, this is y equals mx plus b, but I just reordered the numbers, so it's b plus mx. And if you notice, the arithmetic sequence, when you have the initial value, is exactly the same, where the d and the m represent the constant change in either the sequence or the function. That's our constant rate of change. But then we have a more useful version of these formulas, the arithmetic sequence and linear function point slope version. Again, this is right here, y minus y1 equal to m times x minus x1. And you're probably like, Ms. Quigley, that says yi and xi. I agree. It's because you can use any coordinate pair. It doesn't have to be the first one or second one. It can be the third or the fourth one. So the I is just a placeholder for any number whatsoever that you can plug in there. So again, the important things to point out here is that you still have a slope and a common difference that are the average rate of change that is constant for these functions. But then you have a coordinate point, x comma y, or k comma a sub k, that you can plug into the formula. This is what we did last class, but now we're just applying it to linear functions instead of sequences. In the same way, we can do the same sort of highlighting for geometric sequences and exponential functions. These sorts of things do not have common differences, they have common ratios. That's why we use the letter R. Now in an exponential function, we would have called that the base. And so base, we use B for base. It's the common ratio, it's the proportional change in these sequences or in these functions. So both the initial value version, where you don't have to subtract a letter k, and the point slope version, which is air quotes point slope, that's not really what it's called, but it works that way, where you have the common ratio or the base, and you have some coordinate point x1, y1, or k and g sub k. These all work the same way. In fact, you can think of them interchangeably, sequences and functions. The only thing we know for sure is that sequences you don't connect the dots with because it's just numbers, but functions you will connect the dots because we can use all real numbers to plug into a function where we can only use whole numbers in a sequence. Okay, but it is important to understand the similarities and differences between linear and exponential functions, which is really the change and the differences we're looking for today. So again, my linear functions act like those arithmetic sequence, and my exponential functions act like those geometric sequences. Now we have the two formulas here. They both have a way they are changing. Linear functions, again, change at a constant rate. They have a slope, so we have a constant rate of change. But because we are multiplying in exponential functions by this base value, by the common ratio, that means that the output values change proportionately. And I will tell you right now, we're going to be writing down the word proportionately as an explanation, kind of like we talked about constant rate of change. Proportionately is one of the words I cannot spell correctly no matter what I do, so please ignore the fact that I'm going to spell it wrong, and you please spell it wrong. It's just one of those words that doesn't stick in my brain, and I can't spell it right. Just warning you right now. Yeah, Worcestershire or necessary. Those are really hard words for me to spell, and I don't get it. See, but I stress about what is the double S or double C, which ones come first, which comes second, which one is doubled. I don't know. I get panicked. But it's great because you can just use the word needed instead, so it's never necessary to use the word necessary. Boom. For linear functions, the change or that slope is based on addition. So when we were doing this sequences, we added these numbers every time. That's how linear functions are created, by adding the same difference every single time, adding that common difference. But your base, the change in a exponential function, is going to be based on multiplication. In geometric sequences, that was when we multiplied or divided, which is multiplying by a fraction, to change from one number to another, which is a proportionate change. But in either type of equation, as long as you have 2 points, you can write the equation of a linear function to solve for the equation for both an exponential function, linear function, or the two types of sequences. So as long as we have 2 points, we can find the common difference or common ratio, the slope or the base, and we can go from there. Okay, part of the goal of today is to be able to recognize when your data tables are now showing you an exponential change as opposed to a linear or a quadratic change, which is what we did in Unit 1. So if you look on the back, we have tables again. What's up? Yeah, go ahead. We have tables again, and we want to figure out what type of data is represented in these tables. So first thing to notice is that in this table, do we have equal length input value intervals? Yeah, they're all +3. So we can just look at the outputs to see what's happening. And if I just check the outputs here, what's the pattern happening going from 7 to 5, 5 to 3, 3 to 1? Yeah, each of these is subtracting 2 each time. Since I'm using addition, which is adding a negative, so it looks like subtraction, that means that this function is probably going to be linear. Because over equal length input value intervals, the output values of f of x change at a constant rate. That's exactly how we answered things in Unit 2. And just for bonus, we're going to say -2. That's our constant rate. Right? We've done questions like this before. We've answered questions like this before. Easy peasy, lemon squeezy. In the B table, are those input values changing over equal length input value intervals? Great, so this is an easy question. If we look at the pattern of the outputs, first thinking about addition and subtraction, how do you go from 1 to 2?
1.
How do you go from 2 to 4?
2.
Okay, pause, because it's not the same number, right? We're not trying to decide if this is quadratic, so we're actually going to stop. Can we use multiplication or division here? Yeah, what can I multiply by here? Times 2, times 2, times 2, times 2, which means that this table is probably going to be a function that is exponential. Because over equal length input value intervals, the output values of, this should say h of x, oops. The output values of h of x change, and then good luck, Miss Quigley, proportionately. Did I spell it right?
Yeah, that's how you
Did I spell it wrong? We're going to leave it like that. Just know it's supposed to be spelled correctly. It's just one of those words I'm never going to get right.
Yeah,
I panic if there's an E or not an E. Does the E go after the L or before it?
TE is not as negative.
Thanks, girl. I misspelled the word rumble in the 3rd grade spelling bee, and I've just been traumatized ever since. Did I spell it right? Proud of me. Chewy, don't do that to me. Okay. Can you guys tackle tables C and D for me? And there is a typo in C. This should say G of X, my bad. Okay, I want you to do those 2 tables. Try to determine what type of data would be represented by that data set. What did you guys notice about table C? It's neither, because we could not find a constant rate of change nor a constant proportional change. It is neither going to be linear nor is it going to be exponential. So the reason that you would give here is literally just that. This function could be neither because over equal length input value intervals, the output values of g of x do not change at a constant rate. That's the linear version. Nor does it change proportionally. Proportionately. Ooh, I'm getting good, I think. Nice. Good job, me. Okay, for the last table there, I know you're still writing that sentence probably, but what did you guys get for the type of data in table D? Yeah, each time you're doing this, we're multiplying by a half, which is dividing by 2, but we want to start thinking in multiplications only. So if you're wanting to divide, that's just the fraction version of what you're wanting to divide by, which means that this function could be exponential because over equal length input value intervals, the output values of k of x change proportionally. Still looks wrong. You know, it's just one of those words that I'm going to stress about for the rest of my life. It's fine.
It's because the E.
It looks wrong, right?
Yeah.
I don't know.
English is
hard. It is my first language, but it is hard. Okay. So we have now a new option when we're looking at tables. In Unit 1, our options were linear, quadratic, cubic, quartic, fifth degree, sixth degree polynomials if we looked at the differences. But now if you cannot find a pattern in the differences, you could also check proportionality. You can check to see if it's multiplication or division. So we have a new option for the type of data we could have in a table. Example 2 is going to tie in our sequences with our functions. It says, a wild rumor is spreading that Miss Quigley won 3rd place in the world's coolest teacher contest. What? The number of people that have heard the rumor can be modeled using a geometric sequence. We need that information, geometric sequence, where 43 people had heard the rumor on day 3 and 140 people have heard the rumor on day 6. According to the model, how many people, to the nearest whole number, have heard this awesome rumor by day 10? So here's what I want us to do. We're going to need to use the information they gave us to create 2 coordinate points so that we can plug it into the formula. So if we read this question again, it says 43 people had heard the rumor on day 3. That means that we would say G of 3, or G sub 3, sorry, is equal to 43, because 43 people had heard the rumor day 3. What would the coordinate point look like if for the 140 people have heard the rumor on day 6? Very good. G sub 6 equal to 140. Input value of 6, output value of 140. What we're going to do is we're going to assign these to be G sub k and G sub n in my formula. And because the formula is on the other side of the paper, we're going to write it down. Normally, the formula for a geometric sequence given 2 points is G sub n equal to G sub k times r to the n minus k. This is from the front side. The 3 things we need to fill in here are the common ratio and the coordinate point k and G sub k. Now, of course, we don't have the common ratio yet. So we need to use both coordinate points to find the common ratio. Now, I specifically picked this one to have the G of k be the smaller number and the G of n be the larger number. I recommend doing that because it's a little bit easier to work with in general. So if we start to say that again? Oh, that wasn't to me. If we start to solve this, this would be 140 equal to 43 times r, we don't know that one yet, to the 6 minus 3. Now, especially when it comes to geometric sequences, do you notice that 6 minus 3 is a positive number? And if I had reversed those, it would be 3 minus 6 would be a negative number. Just in general, we want to avoid negative exponents because it's just a slight more complication. It's not wrong. It's just a little bit more challenging. So we're going to avoid. We're going to try to make our exponents positive. So that's why I assigned the bigger number to be n and the smaller number to be k. If I start to reduce this, and we're not going to type anything into our calculators. Oops, you needed your calculators today. Pause, we'll get them in a second. We're going to do all of this by hand first and type things into the calculator once, which means when I divide by 43 on both sides, I'm not actually going to divide by 43 yet. I'm just going to act like I'm dividing by 43 on both sides. Not type it in a calculator because it's going to give you some ugly decimal, and we don't want to lose the specificity of our numbers. 6 minus 3 is 3. Cool. How do you get rid of that cubed? Cube root, which means that r would be equal to the cube root of 140 divided by 43. Okay, I'm not even going to put that in a calculator yet because, again, that would be some sort of decimal. And I don't want to round too early. We round only at the very end of problems in this class. But we have found that common ratio. It's whatever the cube root of 140 divided by 43 is. Some number. We don't type it in yet. But now we can go back to this formula and plug in the yellow and the blue, which means my formula would now say G sub n equal to 43 times the cube root of 140 over 43 raised to the n minus 3 power. Yes, so to answer the actual question here, because I want to know how many people have heard this awesome rumor on day 10, that is asking me to actually calculate G sub 10. So I would do 43 times the cube root of 140 over 43 raised to the 10 minus 3 power. And this is definitely a question you want to ask to a calculator because that's pretty gnarly to write down. So please elect someone from your team to go get a couple calculators so not all 30 of us go get a calculator at the same time. I'm sorry, I forgot to tell you to grab one. We'll pause for a second, go grab a calculator. So now that we have our calculators, we need to type all of this in at one time. Okay, we don't want to round to the very end of these kinds of problems because we lose specificity of numbers. And we don't want to round too soon and then use the wrong number later. So we got to remember how to type all this in. But I know that we were working on some SAT questions last time and a lot of you found the cube root button. Does anyone remember where the cube root is? Math. And then 4? I think so. 4 or 5? 4. I have a calculator right here. Math 4 is the cube root button. So you will do 43, open parentheses, math 4, and then maybe make a fancy fraction. 140 over 43, get out of it, close parentheses, to the 10 minus 3. We press enter. I'll give you some time to type. Let me see. Whoa, what is happening here?
Oh, 15 points. What did you get?
Okay, what did you guys get when you typed it in? 675.57, but it does ask us to round to the nearest what? Whole numbers. So there's approximately 676 people who have heard this awesome rumor by day 10. What? Cool. So this is exactly what we did last time. It's just going to get more and more complicated because we're going to apply it to different situations that functions better defined as opposed to potentially just sequences. This one was still a sequence, but it acts just like an exponential function. Can we do another one of these? Great. This next one says, a large theater has rows of seats where the number of seats in each row can be modeled by an arithmetic sequence. If the fifth row, let's highlight that, arithmetic. Arithmetic acts like a linear function. We're more comfortable here. If the fifth row has 31 seats and the 11th row has 49 seats, determine how many seats there are in the 25th row. So we still need 2 coordinate points. What would the 2 coordinate points be for this question? Great. Fabulous. Now again, I want to be able to keep positive numbers here, so I'm going to assign out of these two, the bigger one to be a sub n and the smaller one to be a sub k. It's just in general, I want to keep positive numbers, especially for geometric, but might as well do it for arithmetic as well. Now again, the formula is on the other side of this paper, but hopefully it's starting to look familiar. A sub n equal to a sub k plus d times n minus k. The 3 things we need to fill in here are the common difference and then my 2 coordinate points, well, the x1 and the y1, or the k and the a sub k. We have k and we have a sub k. Do we have the common difference? No. Darn, so we have to solve for it. So we plug things in. This would be 49 equal to 31 plus that common difference times 11 minus 5. Again, it's not wrong if you end up working the other way where the numbers are negative. It's just a little bit easier if you can see ahead to keep your numbers positive. If we're starting to solve for D here, I would subtract 31 from both sides. 49 minus 31 is 18. And then 11 minus 5 is 6. Solve for D, what's the last step here? divide by 6. Because these came to be whole numbers, I went ahead and actually did the math. But if 49 minus 31 for some reason was some sort of decimal or fraction, we'd want to leave it. And then if the dividing was some sort of decimal or fraction, we'd want to leave it as the fraction because we want to keep the specificity of our numbers. So again, we have our common difference. This one was nice and easy because these were numbers we could do in our head. But then we have to go back and we actually fill in this formula. We would fill in a sub n equal to 31 plus 3 times n minus 5. Again, we put back the k and the a sub k as the numbers, but we leave the n and the a sub n like we would leave x and y in a normal linear function. Now I can't help myself here. We're going to distribute. This would be 31 plus 3 times n minus 15. What's 31 minus 15? 16 plus 3n. That's just an easier function to work with when we're starting to plug stuff in. But we're wanting to know how many rows are on the 25th seat of this theater, which means we're plugging in 25 to the formula. What is 3 times 25? 75. And then 16 plus 75? 91. So there's 91 seats in the 25th row of this theater. So it feels like this is exactly what we did last class, and it should, because sequences and functions work the same way. So whether they tell you in problems like 2 and 3 that it's a sequence or it's a function, you would treat it the same. You're just changing the formula you're using either from being the sequence version, like we did here, to the exponential function version or the linear function version, which is just next to it on the table on the front of these notes. So the skills are transferable to both types, a sequence and a function. Yes? All right.